Hello everyone, my name is Akesh Sohan and we will be learning how to do proofs by induction. So the idea behind mathematical induction is seen in this visual here with an analogy to knocking over dominoes. So if each domino represents a statement, and let's say the first statement's knocked over. In this case, the analogy means that the first statement's proven true. And now if the first domino falls, all its successive dominoes after it means it will fall. So in this analogy, all the dominoes have fallen, so that means you've proven all statements to be true. And that is how induction works. And in this presentation, we're using sigma notation. And in this particular statement, n equals 1 to 4. And so you plug in your n values into this equation. So it'll be a 1 in your first statement, and it will go up to 4. So you plug in 1, and then a 2, 3, and 4, and that sums to 10. And this is the equation that we will be proving through induction. The sum from k equals 1 to n of the equation being summed, k times k plus 1. That equals n times n plus 1 times n plus 2 divided by 3. So now, for our base case, you have to prove a starting point where statement 1 is true. And oftentimes this can be done through evaluation. So for our base case proof, using our original equation, you set n equals 1 as your starting point. And if we plug that into the left side of the equation, k equals 1 to 1, and that means you will only be summing one term. So if you plug in a 1, 1 times 1 plus 1 is 1 times 2, and that is 2. If you check the right side of the equation and you plug in a 1, it's 1 times 1 plus 1, which is 2, times 1 plus 2, which is a 3. The numerator is 3 times 2, which is a 6, and then when you divide that by 3, you get 2. So now does the left side equal the right side? Yes, it does. So this proves that the base case works. So now for our inductive step, we have to prove that for one statement, it implies that the successive statement is true for positive integers. And in the inductive step, you assume that sk, your current statement, is true. So this is our original statement here, and we're proving through induction that the current statement implies that successive statements are true. And so if we set n equal to k, our equation becomes this. So let me explain. The sum of k equals 1 to 1 plus your current statement, which is right here, is being summed, and that is equal to your original equation right here, which we're assuming to be true, plus 1. So when you have a k plus 1, you have to look wherever you have a k in your original equation and put k plus 1. So k plus 1 right here. And then for this k, it's a k plus 1, and you just add the 1. So now if we simplify the equation, it's equal to k plus 1, k plus 2 over 3. And that's just substituting this original equation. And this is k plus 1 right here, k plus 1 plus 1, that is k plus 2. And you can do 3 over 3, which is equal to 1, just so that you can have like denominators and add these fractions. And that is equal to this, k plus 3, k plus 1, k plus 2 over 3. Because these two terms, k plus 1, k plus 2, are similar. So you just add like terms, k plus 3, which is right here, divided by 3. And this right-hand side is equal to the left-hand side, and this concludes our proof through induction. And just to show you guys that these equations are equal, I provide an example here. This is our inductive step equation we derived. If let's say you plug in k equals 3. On the left hand side, you're summing from k equals 1 all the way up to 4 because it's a term after 3. So when you plug in your values, you get 1, 2, 3, and 4, and you just multiply them out and you will end up with 40. And on the right hand side, you just plug in 3 as well, and you have 3 plus 3, 3 plus 1, 3 times 2, which is 6, 4, and 5. And you multiply those out and you get 120 divided by 3, and that's also 40. So now this shows that this equation does indeed work. And for my references, I reference Mark Bodie's presentation on induction. And this concludes my presentation on proofs through an induction. So thank you very much.